Hey everyone, and welcome to this brand new series on transformers, one of the most revolutionary ideas in modern artificial intelligence. In this course, we'll explore why the transformer architecture was created, what problems it solves, and how it powers today's most advanced AI systems like ChatGPT. We'll start from the very basics of language models, move through traditional approaches like recurrent neural networks and LSTMs, and then step into the world of transformers with concepts like embeddings, self-attention, and parallelization. By the end of this series, you'll not only understand the theory, but also see how transformers change the game in natural language processing and beyond. So let's get started. Let's begin with the big question. Why do we even need transformers? Think about a simple conversation. If I ask you, "How are you?" You'd probably reply, "I'm fine, thanks." That's a basic example of a language model, a system that can understand context and respond meaningfully. Earlier, we tried to solve this using recurrent neural networks or RNNs, and later with more advanced versions like LSTMs and GRUs. These worked well for short and simple sentences. But when the text became long, say trying to understand the connection between the first and last sentence of a paragraph, these models began to fail. Transformers were introduced to fix this problem, allowing models to remember and connect words and concepts no matter how far apart they are in a sentence or even across paragraphs. Now let's slow down and really understand why RNNs and LSTMs, which were once state-of-the-art, just aren't enough for the kind of powerful language models we want today. So first, imagine RNNs or recurrent neural networks. They process text one word at a time in order, just like you reading a book word by word. That sounds natural, right? But here's the catch. Every time an RNN reads a new word, it has to remember what came before. Over time, that memory starts to fade. This leads to what we call the vanishing gradient problem. Here's a simple analogy. Think of passing a message down a long line of people, like the telephone game. The first person whispers a sentence to the next, who whispers to the next, and so on. By the time the message reaches the last person, it's distorted or completely lost. That's exactly what happens in deep RNNs. The information from the early words gets weaker and weaker as it moves forward through the network. LSTMs, or long short-term memory networks, were designed to fix this. They use special gates, kind of like filters, that decide what information to keep, what to forget, and what to pass forward. This helps them remember better than plain RNNs. For short or medium-length sentences, LSTMs can do a great job. But here's the problem. When the context is very long, like a full paragraph, an entire article, or even a book, LSTMs still struggle. They can capture some long-term patterns, but not all. For example, in the sentence, "The dog that had been running in the park since morning finally laid down to rest because it was tired." The word dog and the word tired are far apart yet connected. An LSTM might miss this link because the middle words distract the model. There's another limitation too. RNNs and LSTMs are inherently sequential. That means they read one word after the other, like following a single train track. This makes them slow to train because they can't easily use parallel computing. Imagine trying to read an entire book but only being allowed to see one word at a time. It would take forever. That's why training big models with RNNs and LSTMs is computationally expensive and slow. Finally, in the real world, we often deal with huge amounts of text, with long-distance dependencies, sudden changes in topic, and complex relationships between words. Traditional RNN-based models just aren't equipped to handle that efficiently. So, even though RNNs and LSTMs were groundbreaking in their time, they simply hit a wall when it comes to scaling up to the kind of massive language understanding we need today. And that's why the transformer architecture was born, to solve these exact problems with a more elegant, parallel, and powerful design. Alright, now that we've seen the limitations of RNNs and LSTMs, let's talk about the hero of our story, the transformer. Transformers were introduced in 2017 by Google researchers in the famous paper, "Attention is All You Need." And the title wasn't just catchy, it was revolutionary. The idea was that we don't actually need recurrence, we don't need convolutions. What we really need is attention. So what's the big deal? Well, unlike RNNs, which process text word by word in sequence, the transformer looks at the entire sentence at once. Imagine reading not one word at a time, but the whole sentence in a single glance, like scanning a paragraph and instantly spotting the keywords that matter most. That's what makes transformers so powerful. At the heart of this is something called self-attention. Think of self-attention like a spotlight. When the model is trying to understand a word, it shines a spotlight on all the other words in the sentence and asks, which ones are most relevant to this word? For example, in the sentence, the cat sat on the mat because it was tired. The word "it" should be linked back to cat. Self-attention allows the model to make that connection directly, no matter how far apart the words are. Another game-changing feature of transformers is parallelization. Remember how RNNs had to process word by word like a single-lane road? Transformers, on the other hand, are like a multi-lane highway. They can process all words in a sentence at the same time. This massively speeds up training because modern GPUs can handle lots of data in parallel. That's why we were suddenly able to train huge models with billions of parameters, something that was impossible with RNNs. And here's the fun fact. This architecture didn't just improve language models, it became the foundation for almost every modern AI breakthrough: machine translation, text summarization, question answering, and of course, large-scale models like ChatGPT. All of them are powered by transformers. So in short, transformers solve three big problems at once. 1. They handle long-term dependencies using self-attention. 2. They train much faster thanks to parallelization. 3. And they scale beautifully to massive datasets and models. That's why the transformer is considered a turning point in AI history, the moment when we truly unlock the ability for machines to understand language at scale. Now let's take a step back and look at the roadmap of this course. This isn't just a single lecture, it's a full journey, carefully designed to take you from beginner-friendly foundations all the way to advanced, real-world applications of transformers and large language models. We'll begin with Module 1, Foundations of Transformers. Here, we'll build the ground knowledge you need. You'll learn why transformers were such a revolution in AI, starting from simple word embeddings and moving toward contextual representations that capture meaning. We'll explore positional encodings, which allow models to understand word order, something that's not obvious when processing everything in parallel. We'll dive deep into the self-attention mechanism with visual explanations, learn why masking is essential during training, and see how multi-head attention gives the model multiple perspectives at once. Finally, we'll break down the anatomy of a transformer block piece by piece. In Module 2, Encoder-Only Architectures, we'll explore models like BERT. You'll see how encoder-based transformers are great for understanding and analyzing text. We'll cover the famous CLS token and how it's used in classification tasks, the difference between pre-training and fine-tuning, and how variants like Roberta improve on the original BERT. And yes, we'll get hands-on with practical tasks like sentiment analysis, text classification, and question answering. Then comes Module 3, Decoder-Only Architectures, which power today's large language models like GPT and Llama. We'll see how these models are structured, why they use autoregressive training objectives, and how they generate text one token at a time. We'll also cover fine-tuning methods like full fine-tuning, LoRa, and QLoRa, essential for making large models more efficient. And we'll introduce reinforcement learning with human feedback, RLHF, the technique behind models like ChatGPT. You'll even try customizing your own decoder-only model for text generation. Next, in Module 4, Retrieval Augmented Generation, or RAG, we'll step into one of the hottest topics in AI today. You'll learn the problem it solves, giving language models access to external knowledge. We'll cover embeddings and semantic search, introduce vector databases like FACE, Pinecone, and Weaviate, and explain approximate nearest neighbor search methods like HNSW and LSH. To bring it all together, we'll build a full RAG pipeline for a real case study, asking questions about a PDF document. Module 5 is all about prompt engineering, often called the new programming. You'll see how the way you phrase a question can completely change the model's answer. We'll explore zero-shot, few-shot, and chain-of-thought prompting, as well as prompt chaining for tackling complex tasks. And of course, we'll discuss best practices and limitations so you can prompt models effectively. In Module 6, under the hood of LLMs, we'll peek inside the engine. We'll start with tokenization and vocabulary building, then compare different training objectives like masked language modeling versus causal modeling. We'll dive into the math of attention, queries, keys, values, and dot products. But don't worry, I'll explain it step by step. We'll also cover optimization tricks like AtomW, learning rate schedulers, and gradient clipping, along with regularization techniques to avoid overfitting. Finally, we'll discuss evaluation metrics like perplexity and accuracy and see how researchers benchmark these models. Then, in Module 7, Advanced Topics and Responsible AI, we'll look at inference strategies such as greedy decoding, beam search, and probabilistic methods like top K and top P sampling. We'll explore scaling laws and the trade-offs between data, compute, and performance. Importantly, we'll also talk about model interpretability, explainability, and the critical issues of bias, fairness, and responsible AI use. And of course, we'll end by looking at the future of transformer architectures. Finally, in Module 8, Practical Implementation with PyTorch, we'll roll up our sleeves and code. You'll build embeddings and attention layers from scratch, implement a mini transformer step by step, and train a small language model on custom text. We'll also practice fine-tuning using LoRa and QLoRa, and finally, we'll deploy a lightweight model for a real application. By this point, you won't just understand transformers, you'll be able to build, train, and use them in your own projects. So, by the end of this course, you'll go from learning why transformers exist all the way to actually implementing and applying them. This way, you won't just watch history, you'll become part of the new AI era yourself. So before we wrap up this introduction, let me share who this course is designed for. If you're a beginner who's just curious about AI and wants to understand what's happening behind the scenes, this course will give you a gentle yet powerful start. If you're a student or researcher, you'll find all the key concepts and mathematical foundations explained step by step so you can build strong expertise. If you're a developer or engineer, you'll learn not just the theory but also the practical skills to build, fine-tune, and deploy transformer-based models in real projects. And honestly, if you've ever wondered how tools like ChatGPT, translation systems, or AI assistants work, this course is perfect for you. If you find this content helpful, don't forget to hit that like button, subscribe to the channel, and click the notification bell so you don't miss the upcoming modules. And of course, share this with a friend or colleague who wants to learn about AI, because the more people understand transformers, the more fun and powerful our community becomes. Alright, that's it for our introduction. In the next lecture, we'll jump straight into the foundations of transformers, starting with word embeddings and positional encodings. See you there.